Welcome to lecture 2. In this lecture, let's continue our discussion on chemical periodicity and the properties of chemical periodicity. So let's start with electron affinity. So what is electron affinity? Electron affinity is the energy change that occurs when 1 mole of electrons is added to 1 mole of gaseous atoms or ions. Now, when you have atoms with low electron affinity, they tend to form cations, and the atoms with high electron affinity tend to form anions. Now, the trends in this electron affinity is generally not as regular in terms of the similarity to atomic size and ionization energy. So they are not similar because here electron affinity is the energy change here, and because it's the energy change, when you're adding electrons, there are chances that some atoms behave differently than others. So this causes a small shift in some of these values. For example, if you look at some of the values, you notice that in general, the values tend to be going downward, so the values tend to be increasing. But the chances are that sometimes it can also be having some peculiar behavior, for example, like aluminum. And even in the periods, you have a peculiarity here. Notice that it's higher here and then much higher here and then much lower again. So there is a bump in these values that you generally see. Now, in terms of the behavior patterns between ionization energy and electron affinity, remember that ionization energy is exactly opposite to that of the electron affinity, because ionization energy is the energy required to remove 1 mole of electrons, and electron affinity is the energy required to add 1 mole of electrons. Now, when you have reactive nonmetals, they generally contain high ionization energies and they have highly negative electron affinities. And these elements generally attract electrons strongly and they tend to form negative ions in the compounds. Most common non-metals are the last group of elements that you generally see, 7A and 6A group elements. That's the reason why you notice that the electron affinity values are really high there. Next, you have reactive metals. So metals are generally the 1A group and the 2A group elements. So these group of elements generally have low ionization energies and slightly negative electron affinities. So these are the electrons that these elements lose electrons easily and they tend to form positive ions in ionic compounds. Next, you have noble gases, which are the most peculiar out of them. So noble gases are elements that have very high electron ionization energies because they are already stable, but they have a slightly positive electron affinity. The reason they have a slightly positive effect is because these elements neither lose or gain electrons. So because of the high electron affinity and high electron affinity and high ionization energies, they generally tend to have very little movement in terms of the electrons, in terms of addition or removal. Now, in terms of the trends in the atomic properties, the atomic size decreases down a period and increases down a group. It decreases across a period and increases down a group. Ionization energy increases across the period and decreases across the group, decreases down a group. Electron affinity in general, it should generally decrease. So it generally decreases down a group and increases across the period, but that has many exceptions because some elements might have low and very high ionization electron affinities. Next, let's talk about metallic behavior. So metallic behavior in terms, what are metals? Metals are basically typically shiny solids with moderate to high melting points, and these metals are generally very good conductors of heat and electricity, and they can be easily shaped because metals are ductile. So the ductility is a property of material to be able to bend and use it in any shape or form needed. Now, metals tend to lose electrons and form cations, and they are generally easily oxidized. Now, metals are generally strong reducing agents, and most metals generally form ionic oxides, which are basic in aqueous solutions. So remember this, that most metals always form ionic oxides, and they are strong reducing agents because they undergo oxidation very easily. So when you say strong reducing agent, it is basically reducing another quantity by undergoing oxidation. So remember the idea here. Now, in terms of the metallic behavior, when you go down the group, the metallic behavior increases, but as you go across the period, you notice that the metallic behavior actually decreases, where you start with very reactive metals towards very reactive, unreactive non-metals, or most commonly noble gases. Now, next let's talk about oxidation numbers. So oxidation numbers we generally use high and lowest oxidation numbers of the main group elements are shown here. And 1A and 2A group elements have, 1A group elements generally have an oxidation number of +1 and 2A generally have +2. The first three generally are always positive oxidation numbers. The reason mainly is because they are ready to donate electrons. But from 4A to 7A, these are elements that undergo either oxidation or either have positive or negative oxidation numbers depending on the element that bonds with them. Even hydrogen has two different oxidation numbers in its existence. Now, in terms of the acidity, so when you take calcium oxide, the calcium oxide is the oxide of the main group metal, so which means it is going to be strongly basic. And when you have phosphate P4O10, the oxide of a main group non-metal is generally acidic. So the main group metal is basic, strongly basic, and main group non-metal is strongly acidic. Now this is what we call the acid-base behavior of oxides. Main group metals generally form ionic oxides. These are generally very basic. And main group non-metals generally form covalent oxides, which are generally acidic. Now some metals and metalloids can form amphoteric oxides, which act as both bases and acids at the same time. For example, aluminum oxide is an example of an amphoteric oxide where it can react with an acid as well as it can react with a base. So this is the structure here. So in terms of the acid-base behavior, across a period, the acidic behavior, so it becomes more and more. So when you start from strongly basic towards strongly acidic, and down a period you start going from strongly acidic to strongly basic. This is dependent on the metal behavior as well, because the more metallic the atom, the more ionization and ionic oxide it forms. If it forms covalent oxides, it becomes more acidic. Next, let's talk about electronic configurations of monatomic ions. So when you have an ion, how do you write the electronic configuration there? So elements at either end of the period can gain or lose electrons to attain a filled outer level. So the resulting ion will have a noble gas electronic configuration, and this generally is called as isoelectronic configuration with the noble gas. For example, when you take sodium and you remove one of the electrons from that becomes Na+, which has the same electronic configuration as that of neon. Remember that it does not have the same number of protons, but it does have the same number of electrons as that of neon, which is a sign of stability. That's the reason why most elements form ions. Next, if you take bromine here, when you add an electron to bromine, it becomes Br-, which is isoelectronic with krypton, so which is another noble gas configuration which the bromine achieves due to addition of an electron. Now the behavior can be described based on the placement of the atoms. The atoms after the noble gas generally tend to lose electrons. The atoms before the noble gas generally tend to gain electrons. The reason mainly is because the elements 6A and 7A here want to achieve electronic configuration of noble gases. The same thing with 1A and 2A elements, they want to lose electrons and achieve the electronic configuration of noble gases. Next, you have a pseudo noble gas configuration, which is generally attained when you have a metal ion empties its highest energy level. For example, when you take stannum, which is tin, and if you remove 4 electrons from the 5th orbit, you notice that it becomes fully filled until the d orbital. But here it is not isoelectronic with any other noble gas, but it is still stable. This is called as a pseudo noble gas configuration, and it is more common for transition elements. So it's more common for transition elements. So use the same principles now. So pause the video right here and try to write the condensed electronic configurations and what would be the ions that it can form. Remember that you have to remove the electron or add an electron based on the proximity of a noble gas to that atom. So pause the video right here and try to write the condensed electronic configurations and form the common ions that can be formed from these metals. Next, let's talk about magnetic properties of transition metal ions. So I told you that transition metals have peculiar behavior. That's why we did not discuss using the same theories as main group elements. Because transition metal ions generally exhibit magnetic properties. And a species that generally contains one or more unpaired electrons can exhibit paramagnetism, which is it can be attracted by a magnetic field. When you take silver, silver has one lone pair and 5 different filled pairs. These are just, so because of the presence of this lone pair, silver is slightly magnetic. And when you have a species that with all of its electrons paired, then that is called as diamagnetism. It is generally not attracted or generally sometimes slightly repelled by a magnetic field. So these are some different kinds of metals that you will generally see. So magnetic behavior can provide evidence of electronic configuration of a given ion. So when you take titanium here, titanium originally has some value of 20. Now let's take a look at titanium. Titanium has an atomic number of 22. So it has 2 filled electrons in the 4s orbital and 2 electrons in the 3d orbital. Because notice that it is argon 4s2 3d2. So this is the configuration for a condensed configuration for titanium. Now when you remove 2 electrons and you become titanium 2 plus, you notice that the elements that the electrons that are going to go first are the 4s group elements, and you have 3d containing 2 electrons each. So this titanium here has 2 unpaired electrons and is generally paramagnetic, providing the evidence that the 4s electrons are lost before the 3d electrons. So this titanium 2 plus has 2 unpaired electrons and it generally becomes paramagnetic. Notice that if it has more than one unpaired electron, it is paramagnetic. More than one or more unpaired electrons, it is paramagnetic. Now, it provides the evidence that the 4s electrons are the ones that lose before the 3d electrons, because if it's not paramagnetic, we'll notice that we'll think that these are the electrons that are going to go first when you remove the electrons. But because it's magnetic, we can say that these are the electrons that are going to go out. So use the same principle now. Pause the video right here and try to write down the predict the magnetic behavior of these following atoms. Next, let's talk about ionic size versus the atomic size. Now, cations are generally smaller than their parent atoms, while anions are generally larger. Now, ionic radius will increase down a group as you increase the atomic number, and cation size decreases as the charge will increase. Now, an isoelectronic series is a series of ions that have the same electronic configuration. Within the series, ion size decreases with increasing nuclear charge. So notice that here the ionic size radius will always increase as you start increasing the number of electrons that are being lost there. As the atomic size increases, automatically, as n increases, the charge increases, automatically this also increases. So that's why 3 plus atoms are much smaller in comparison to a 1 plus atom, and a 1 plus atom is much smaller in comparison to a 3 minus atom. So when you lose electrons, you become smaller, the atom becomes smaller. When you gain electrons, the atom becomes large. So next is the ionic radius. Ionic radius obviously is the distance between the radius of the ion on an average. Now this ionic radius versus atomic radius here, notice that the atoms, as they lose more and more electrons, for example 1a group atom only lose one electron. When you take 2a group elements, they can lose 2 electrons, and 3a group elements can lose 3 electrons. So the size starts decreasing rapidly, and when you look at the atoms that can gain electrons, the size increases rapidly. So it decreases rapidly, going from nitrogen, which generally is the largest, towards fluorine ion, which generally is going to be the smallest in that particular sense. So pause the video right here and try to solve these problems and order them in the order of decreasing size. So let me do the first one. First one here is calcium, strontium and magnesium. So all of them have the same 2 plus charge. So calcium, strontium and magnesium. So again, remember that atomic size plays into this. So the largest out of this is going to be strontium. The next largest is calcium and the next largest is magnesium. So strontium is the largest, calcium is the next, and the magnesium is the next. So use the same principle and solve the other two problems. So with that, we end our lecture on electronic configuration and chemical periodicity. I'll see you again in the next lecture.